What is up, amigos? Today we're looking at the airfoil drag. So in the last video we looked at airfoils and the lift production. Now we're looking at the drag. We're going to be going through the drag curve, something called the drag bucket, as well as the different components of drag. So profile drag, pressure drag, friction drag, and induced drag, or lift-induced drag. So let's get started with the drag curve. Let's say I have a regular airfoil here, and if you watched the last video, you'll know what this means. And to the right here, I'm going to draw the graph showing the drag of this airfoil with different angles of attack. So this is 0 degrees here, AOA. We'll put 5 degrees here, 10, and 15. Then on this axis, we're going to be going from 0 up to about 1. It can be higher than this, but we're going to just say 1 for now. So we have maybe about 0.1 here. Now, for a typical well-designed airfoil, for example, a NACA 0020, a NACA 0012, 4412, 63, 415, whatever. These are just different types of airfoils, Clark Y airfoil, whatever. We are going to have the drag looking like this. It's going to be very low, and then it's going to start to increase quite rapidly. So at this point here, really depending on the airfoil, I should put CD here actually, just for completeness sake. At here, at 0 degree angle of attack, most airfoils will hover around 0.02 to 0.04, depending on the airfoil. So it's a very low drag. Like to get an airfoil, to get something this low drag is quite a feat, and airfoils have been doing it for decades. So well done to them. Now, as we increase angle of attack, so this airfoil starts to pitch up, the drag starts to increase a little bit, not a lot, but a little bit, and then we get to a point where it just starts to skyrocket. And this region here is called the drag bucket. And in fact, if we were to have an airfoil which is symmetrical, so there's no camber, and if you watched that last video, you will know what that means, then this graph here will be symmetrical on this side. So if we go to negative angle of attack or pitch down, this graph will be exactly the same. If this airfoil has camber, then this will not be symmetrical. But back to this drag bucket phenomenon. Now, to understand what this drag bucket is and why it occurs, we need to understand the drag and the different types of drag. So the drag bucket really just refers to this point where the drag is like in a bucket. So if we were to have this side, you can see it's in a bucket region. So why does it occur? Well, to understand this, let's talk about the drag of an airfoil. We have an airfoil here, and we have a few different components of drag. Let's say the airfoil is 2D, so there's no wing tips to it. Then what we have is something called pressure drag and friction drag. What are these two different types of drag? Because they are two different types of drag, which are grouped into something called profile drag, or parasite drag is another word for it. So pressure drag refers to the pressure differences along the airfoil. So pressure can only ever act perpendicular to a surface. But if you notice, the surface is never really completely horizontal or completely vertical. So that means that the surface is always at some sort of angle, and you can decompose the force that this pressure exerts on this airfoil into the lift component and the drag component, depending on the airfoil's orientation. So because we have a difference in pressure around this airfoil, if we were to integrate the airfoil around, the pressure around the airfoil in accordance with the decomposed direction to the drag, we will then get a certain force resisting the airfoil. And this is because when we have the flow coming in, we have quite high pressure here, for example. Then at the back, we have fairly low pressure. And all around, we have changes in pressure. And we'll go into other videos as to why this occurs. But just for now, we understand that there's a difference in pressure as we go along the airfoil. And unfortunately, if we were to integrate the entire pressure around the airfoil, we will get a net drag force. So a resistive force. So that is pressure drag. Friction drag occurs because it happens with anything. Let's say we have any surface, a flat surface, and we have the flow going over it. We have resistance between this surface and this flow, and this is because of viscosity. So this is friction drag, and every airfoil has pressure drag and friction drag to some extent. For a two-dimensional airfoil, typically the pressure drag accounts for about 80 to 90% of the drag, whereas friction drag occurs for about 10 to 20% of the airfoil's drag. So if you have, let's say, the drag coefficient equals 0.1, which is quite high, would be around here somewhere at 10 degrees. The drag coefficient due to the pressure drag, the component of that might be 0.09, and then the drag coefficient due to the friction drag might be 0.01. So if you add both of these together, you get the overall drag. Now that is for a 2D airfoil. And fortunately, this is all we need to know to be able to describe this drag bucket and why we get this skyrocketing in drag. So what happens is at this angle of attack, as we start to increase angle of attack, we have a regular airfoil and the flow flows over, and at 0 degrees, it's quite nice. It just flows over, the entire thing stays attached. As we start to pitch it up and up, so that's how we get to this angle now, the flow comes over and then it'll start to separate. So this region here will start to be a separation zone. And this separation results in a much greater pressure drag. So we have a low pressure in this region, and because we have low pressure at the back on this surface, and we have high pressure here, the net force is back. So we get an increase in the drag, which is unfortunately due to the pressure difference. So it's pressure drag. And as we increase angle of attack more and more of this upper surface starts to separate. So we get a greater increase in pressure drag here. This increase here is largely due to pressure drag. In fact, you could argue, and it does occur, that as you increase angle of attack and more flow separates, the friction drag actually drops because less, like the fluid near the surface, is moving much slower, and slower moving fluid results in less friction drag. But because friction drag only accounts for 10 to 20% of a two-dimensional airfoil's drag, and pressure drag accounts for the rest of it, 80 to 90%, this reduction in friction drag doesn't really have much of an effect overall. It's the dramatic increase in the pressure drag that results in this increasing the overall drag. That's a two-dimensional airfoil. Now let's talk about three-dimensional airfoil. So we have the airfoil like this. We have a wingtip. I'll try to draw a little bit better. Here we go. We have the leading edge here. We have trailing edge here. And we have a wingtip here and a wingtip here. So now we talk about a three-dimensional airfoil. And when we talk about three-dimensional airfoils, we start to incorporate a new type of drag. And this new type of drag doesn't occur for two-dimensional airfoils, and there's a good reason for this. This new type of drag is called induced drag, or more completely, lift-induced drag. And the reason why it's called lift-induced drag is because this drag occurs because we are producing lift. If we weren't producing lift, there would be no induced drag, and let me explain this. So at 0 degree angle of attack, let's assume that this is a symmetrical airfoil, so the lift also equals 0, the lift coefficient. This airfoil is producing no lift. That means the pressure on top is equal to the pressure on the bottom. And from other videos that we've gone into, we know that if there is no pressure difference, there will be no movement of fluid from the top surface to the bottom or vice versa, because there is no pressure difference driving this movement. So that means we don't get any fluid rolling up into a vortex, what's called a wingtip vortex. And that means we don't get any induced drag or lift-induced drag. If we have an angle of attack which is non-zero, let's say it's 10 degrees now, and this airfoil at 10 degrees, let's say it's producing a lift coefficient of 0.9, which is pretty standard. And the drag coefficient is maybe about 0.05. So this airfoil here, even though we do have some flow separation, it still produces quite a bit of lift. So we have a difference in pressures from the bottom surface to the top surface. In fact, the bottom surface has a much greater pressure than the top surface. So because we have a pressure difference as we get to the edges, we now have the fluid can freely flow around from the bottom to the top. And the reason why it would do this is you have high pressure underneath it, like really trying to burst out, and low pressure underneath, which is really trying to suck the fluid in, over on the top, sorry, trying to suck the fluid in. So it's natural for the fluid to move in this direction. And then we'll start to get a wingtip vortex forming. And this occurs because we have lift being produced. So this is a lift-induced drag. And this wingtip vortex is drag because it is wasted energy. We don't really use this wingtip vortex for much. You can use it if you're very clever, but generally speaking, we don't use it. So it's just really wasted energy. And if it's wasted energy, it means it's just drag. It's inefficiency. So that's where induced drag comes into it. And if we were to talk about the drag coefficient of a three-dimensional airfoil, about 40 to 50% of the drag comes from the pressure drag, about 10% from the skin friction drag, and the rest is from the induced drag, so about 30 to 40%. And this depends on the angle of attack as well. The greater the angle of attack, the more induced drag we get, because the more lift we are producing. And the more lift we are producing, the greater the difference in pressures between the bottom surface and the top surface, which drives this vortex and it gets stronger. So that is the induced drag, and the profile drag, pressure drag, friction drag, and the drag bucket. So I mentioned that the drag bucket occurs because as we get to a high angle of attack, we get some flow separation, which increases the pressure drag, and that results in a skyrocketing in the overall drag. So let's cover this just briefly again because we went through quite a lot. This is like literally an entire course in about 10 minutes. So let's cover this again. So we have the airfoil drag, and this is the drag curve here. At 0 angle of attack, most airfoils will have almost no drag. It'll be like 0.02, 0.03 is phenomenal. As we increase the angle of attack of the airfoil, the lift will start to increase a little bit, and then it'll start to skyrocket at a certain point. And this point where it starts to skyrocket, this is the end of what's called the drag bucket. In this drag bucket region, what this tells us is that we can change the angle of attack of the airfoil, and we don't have too much of a consequence in terms of the drag coefficient. So we can really do what we like, and we can get away with it. But if we were to increase it even more past this point, if we were to change the angle of attack of the airfoil, we'll then have to pay the price in terms of the drag coefficient. And this drag bucket occurs because of the pressure drag. So the pressure drag is the drag that occurs on an airfoil because of if you summate the different pressures around the airfoil in the directions that they're pointing and the amount of pressure that there is, you'll find that there is actually overall a net force resisting the movement of the airfoil. So this is a drag. We also have something called friction drag, and this is due to fluid moving over any surface will have this. And you have fluid going over a surface and it's really just shearing along because one fluid is moving at a different velocity to the other, and then that fluid is moving at a different velocity to the wall. And this results in friction due to viscosity. So that's the two different types of drag in terms of a two-dimensional airfoil. For 3D airfoil, we have a third component now called the induced drag, and this occurs because of the wingtip vortices. And this is due to a difference in pressure from the bottom surface to the top surface, which then drives this motion. And the greater this pressure difference, the stronger these vortices will become, and the greater the induced drag. Now, the final component that I want to talk about, which we won't go into in this video, this will be a much more advanced topic, is something called wave drag. And this occurs when we start to get to sonic speeds. So that is the end of this video. If you'd like to, make sure to like it. If you want to see more like this, subscribe. And if you want to get better at CFD and or theory like this, check out courses in the link in the description. And we also recommend a book called Fundamentals of Aerodynamics by John D. Anderson. It's a book I used during my university days. It's really good. I've linked it in the description below. And I'll see you next video. Peace, amigos.